Good morning. So can you hear me?
Yes, sir, we can.
Okay, great. So today is the 23rd of August, Tuesday. I think it's our seventh meeting. Any questions before we get started? I seem to need to download a plugin every time I need to share my screen. Yeah. So last time we began speaking about polar coordinates, in particular plane polar coordinates. So I wish to continue that discussion now. And this is also relevant to the questions in problem set 3 that you are attempting. Okay. Yeah, I hope, yeah, I would like you all to be present on time. Okay, if there are no questions, I will continue where we left off. So remember we set up plane polar coordinates r and theta, which are an alternative to x and y, which are the Cartesian ones, and defined either through x equal to r cosine theta and y equal to r sine theta, or the inverse formula for theta and r in terms of x and y. Okay, and theta was measured counterclockwise from the horizontal axis. And then we extended the notion of the basis unit vectors x hat and y hat to r hat and theta hat. So they were vectors that pointed in the direction of increasing r holding theta fixed, that's r hat, and similarly theta hat. So that is shown in this figure. At any point, you can pick your point other than the origin, because this coordinate system breaks down to the origin. So you pick a point which may have coordinates x comma y. Then at that point, the radially outward pointing vector of unit length is called r hat, and the tangential vector pointing counterclockwise is theta hat. And you will of course notice, as was pointed out by some of you, that the frame xy has been rotated by angle theta counterclockwise to obtain the frame r theta. Okay, so that is another way to view it. Yeah, and that will manifest itself in the transformation formulae as well. Okay, now we made the geometric observation that while at every point x hat and y hat point in the same direction, and that is not the case with r hat or theta hat, generally speaking. Yeah, so what I mean is that at a point, if I have my x hat vector and I parallel translate it to the point of interest, then it will coincide with the x hat vector at that point. Yeah, so I parallel translated there. But that is no longer the case with r hat. So r hat would point this way. Yeah, and you notice that it makes a smaller angle with the horizontal than the r hat that makes over here. So if I parallel translate it, it will no longer coincide with the r hat at the other point. So this is the sense in which r hat and theta hat do not maintain the same directions as you move around. Okay, any question about this basic observation? Oh, fine. We had, of course, obtained formulae for r hat and theta hat in terms of x hat and y hat linear combinations, and that involves cosine, sine, minus sine, cosine. And if you put these entries into a matrix, that would be a rotation matrix by angle theta, counterclockwise. Okay. We of course also observed that r hat and theta hat are orthonormal. By simple calculation, the dot product is 0 and r dot r and theta dot theta are both 1. So that defines an orthonormal frame. Of course, you could invert and express x hat and y hat in terms of r and theta. Yeah. Okay. So this figure, of course, illustrates very explicitly that the direction of r hat depends on location. Yeah, it's changing quite rapidly. Okay. Now moving on, we want to talk about particle motion, and for that purpose, we introduce the position vector r of a particle which is instantaneously located at point P with coordinates x and y. Now that position vector r can of course be written as xx hat plus yy hat because those were the Cartesian components. And then expressing x and y in polar coordinates, we write it as r cosine theta and r sine theta. Those are still the Cartesian components, just expressed in polar coordinates. Now we notice that the vector direction itself can be expressed in terms of r hat. Yeah. So almost by definition of r hat, r is simply small r hat. Okay. So we are back to where we were, I think. Now our aim was to express the velocity of a particle as well as the acceleration. In fact, this is part of question in the problem sheet, but let me just introduce it here at least. So we want to express the velocity of a particle in the polar coordinates and the polar coordinate basis for vectors. So by differentiation of r, you immediately get that r was x hat plus y hat. So differentiating in time, you will get x dot x hat plus y dot y hat. And the main thing is that x hat dot is 0 and y hat dot is 0. These things don't change with location. So in particular, they don't change as the particle moves. That is the main thing that changes in polar coordinates. R hat does depend on location. So the velocity vector, which is the time derivative of the position vector, will have two contributions. When I differentiate this formula, we get an r dot times r hat and then an r times dr hat dt. Okay, so I have asked you in the problem sheet to work this out in more detail. But okay, maybe I will just go through some of this.
What do you mean by more detail?
More detail than what I have spoken right now. That is, I would, okay, let me be more clear. I mean that you want to express dr hat dt as a linear combination of r hat and theta hat. All right. And it's your job to find the coefficients. Those coefficients, of course, depend on r and theta. Yeah, so you are supposed to find those quantities. Is that understood, Ankan? Yeah. So, all right. Let me indicate how this is done. Let us take one example. Let's take the theta hat vector, right? I mean, you're supposed to do it for r hat. Let me do it for theta hat just to illustrate. I take the theta hat vector. Now, by definition, theta hat was this. Yeah, there is a minus sine theta x hat plus cosine theta y hat. So let us start from there. Suppose I want to calculate each time derivative. There are going to be two terms, of course. Differentiating the sine, I get minus cosine. Sorry, I get sine. Differentiating sine, I get cosine times theta dot x hat minus sine theta dot y hat. Okay. Now we make the simple observation. Of course, I'm taking the minus theta dot outside as a common factor. Minus theta dot times cx hat plus s y hat. Okay, where c and s are sine and cosine, cosine and sine. But then we notice that this is simply r hat by definition. Okay, so we have immediately found that theta hat, when you differentiate in time, is given by minus theta dot r hat. So let's take a moment to absorb this formula. See, we have not said how the particle is moving, what causes the particle to move, which way it moves. All that is arbitrary. All you are told is that the particle's trajectory is given by a curve whose location is given by r of t, theta of t. Okay, that's all you're told. These are some arbitrary functions. Based on that information, you're supposed to proceed. Okay, and one finds that one can get an elegant little formula that the rate of change of the azimuthal direction unit vector is minus theta dot r hat. Okay, so one can try to understand this using a figure as well. But any question about the calculation itself? Let us interpret it briefly. First of all, from the formula, we notice that the rate of change of theta hat always points radially. Okay, it has no component in the theta hat direction. Yeah, no component in theta hat direction. Now, can you tell me why I should have expected that? After all, it's some vector, so it should have two components. We have discovered that one of the components is 0. Yeah, so plus 0 times theta hat. So I want you to make a suggestion.
Because it's a unit vector.
Thank you very much. Yeah, who was that?
The Sahil.
Sahil Lakmani. Yeah, so indeed, so theta hat is a unit vector, and therefore its length cannot change. It's unit vector everywhere. Its length cannot change, and therefore its rate of change cannot have any component in the theta hat direction. If it did, then it would mean that theta hat would elongate or contract. Yeah, and that's disallowed. So a good observation. So you can do a similar calculation for dr hat dt. I will leave that as an exercise for you in the homework. All right. Now, okay. So, but any questions about that as to how one proceeds? In fact, I wanted to illustrate this as a picture as well. Perhaps I should do that. Yeah, let's have a look at this picture. Here, the particle was initially located at this point. It moved after a small instant of time to a nearby point. And in that process, well, the picture is oversimplified. It need not, yeah, this is not meant to be a circular motion or any such thing, or rectilinear motion, just an arbitrary little shift. Yeah, and of course, r hat has changed, and so has theta hat. Yeah, so and you can work out how the changes by examining by parallel translating the new r hat vector to the old location. Yeah, and then taking the difference of those two vectors and dividing by the time elapsed. Okay, and the main point is that the difference of those two vectors always points tangentially, because there are two unit vectors at a point. So the difference for small enough angles is always tangential. There cannot be any radial part. Yeah, so so you will conclude that r hat dot must be proportional to theta hat. Okay, it cannot have any component in the r hat direction. Okay. Anyway, this is a part of your homework problem. We can draw a similar figure for theta hat as well and its time derivative. Okay, let me now proceed to the three-dimensional version I mean, there are many coordinate systems in 3 dimensions. One that is of particular interest to us in the study of systems such as the solar system or an atom, is spherical polar coordinates. So there are 3 of them, r, theta, and phi, and they are called the radial, polar, and azimuthal coordinate. Okay, so I will illustrate with a picture so that you understand the reason for the names. So given a point P with Cartesian coordinates x, y, z, the radial coordinate is simply the distance of P from the origin. Okay, so that is given by simple formula. R is simply the square root of x squared plus y squared plus z squared. And we notice, of course, that R is a positive variable, 0 to infinity. Okay, now we need to define these polar and azimuthal angles. Yeah. So let us look more carefully. So suppose P has position vector R relative to a chosen origin, then the polar angle theta, the polar angle theta is defined as the angle that this radius vector makes with respect to the upward vertical z-axis. Okay, so that is illustrated in this picture. This is my position vector, also known as radius vector. You have the z-axis. There is an angle here. Angle between these 2 vectors, that is the polar angle. The reason the name polar is that, well, we think of this as directed towards the North Pole, and this is the angle made with that polar axis. All right. So theta is the polar angle, and it is measured from north downwards. Yeah. So it is 0 when the point lies on the z-axis, upward z-axis. So we can, of course, write theta as cosine inverse of z upon r, okay, because this height is z and this length is r. So looking at that right triangle, this angle, cosine of this angle is adjacent side z by the hypotenuse r. Yeah, so theta equal to 0 corresponds to points in the positive z-axis, and points in the negative z-axis correspond to theta equal to pi. So theta goes from 0 to pi. Yeah, you don't need to go beyond pi because you can go the other way. Okay, any question about how we have defined this polar angle? Okay, now let me go to the next angle, which is called the azimuthal angle, or phi. And this is defined through the following construction. We take the position vector of the point of interest, project it onto the xy plane. Okay, so we project it onto the xy plane. We get some projected vector, which I have denoted through this dotted line here, that projected vector. And that projected vector makes an angle phi with the x-axis, now measured counterclockwise. Okay, so that angle phi is called the azimuthal. Yeah. So please tell me, what is the range of phi?
0 to 90.
0 to 90 is certainly good, but can I go beyond 90?
Yes, sir.
So when you said 0 to 90, I would say that corresponds to points in a particular part of the 3-dimensional space. Can you characterize that part? Okay, okay, we don't need fancy names here, but no, you are welcome to. Okay, see, any suggestions as to the range of phi also? I claim you can go beyond pi by 2.
2 pi.
Pi.
Yeah, you can certainly go to pi. So I mean, if I go up to pi by 2, I will reach the projection would. reach the
Yeah,
y-axis.
if I go to the other side, then pi will you can go to
Correct,
pi.
correct. So I can go beyond. So let's use some proper terminology. The points I've just shown you are arising from this vector lying in the first octant, right? First octant. Yeah, that is x, y, z all positive. But it could also be from another octant that is below the equatorial plane, namely where z is negative and xy positive. So it corresponds to points in two of the
Sir,
octants.
is that line perpendicular, that project that from P to the XY plane?
Yeah, it's dropping a perpendicular. P to the
Oh.
xy plane is vertically downwards. So in other words, this dotted line, which Onkon has pointed out, is parallel to z axis. I hope that clarifies. Yeah, so in a sense, you go infinitely far up to the North Pole, you shine a light, which is thought of as having parallel beams, and that passing through this point P will come and fall over here. Okay, so points in the first and the octant where z is positive or negative, but x and y are both positive, will lead to phi lying between 0 and pi by 2. But you can go beyond, and the total full range, I can go all the way around. Yeah, you notice you can go all the way around. So what is the range of phi, by the way?
0 to pi.
Wait.
0 to 2 pi.
2 pi. Yeah, if I go only up to pi, I would have gone to the negative x-axis. That is as far as I would have reached. But I can go further. Yeah, there are 4 octants in the northern hemisphere. I have to go around all of them. And you will notice that phi equal to 0 and 2 pi both correspond to points where?
Points on XZ plane.
Okay, okay, that's yeah, all right. That's a fine way to say it. Yes. So where the projection lies on the x-axis, so points in the xz plane will have projection on the x-axis. Indeed, very nice. Yeah. So yeah, you said it right. Let me not point correspond to points P on the xz plane. Yeah, so I invite you to please draw this picture yourself and play around with it. Because that is one way to really understand it. But please ask me if you have questions right now about the definitions of these 3 quantities.
Sir, more specifically, plane formed by positive x-axis and z-axis.
Okay, you are pointing out a correction. You may be very well right. A positive z and x, is it?
Positive x and z-axis.
You are right. You are right. Thank you so much. Yeah, negative x would be would be on that side, so that phi would be pi. Thank you. Yes, you're right. So that was Anush Rao, was it?
Yes, sir.
Yeah.
Sir,
XZ plane with positive x. Okay. Yeah. Yes. What was the other question?
sir, what is the difference between theta and phi?
Big difference. Theta is the angle that the radius vector makes with the positive z-axis. Okay, so the positive z-axis, I have my vector, which is denoted by my pencil. The angle that it makes, which I have denoted with my thumb, is theta. That's the polar angle. That's how it's defined. Now the polar angle is 0 when my radius vector points upwards. The polar angle is how much here? What's my polar angle for this vector?
90 degree.
90 degrees. Indeed, pi by 2 or 90 degrees. And now it's gone beyond pi by 2. Yeah, because it's this angle, this angle. So when I go further, I reach all the way pointing downwards, and then the polar angle theta is pi, or 180 degrees. So that is my polar angle. So the polar angle can you give me in terms of geography of the Earth? Polar angle tells you something about which quantity?
Latitudes.
Latitude.
Indeed, yeah. Polar angles are in correspondence to latitudes. Angle theta is related to latitude. Yeah. So the equator is a latitude that corresponds to polar angle theta equal to what?
90 degree.
90 degrees.
Indeed, pi by 2. Yeah. So the North Pole is again a latitude. Yeah, I mean the latitude has shrunk, but the North Pole corresponds to theta equal to 0, and the South Pole is theta equal to pi. Yeah. So okay. So who asked the difference between polar and azimuthal angles? Okay, I've only answered half the question. I hope it is clear what the polar angle. It has to do with latitudes, specifying latitudes. Now, to specify the complete position of a point in three-dimensional space, we need to specify not just the latitude, but also the longitude. And that longitude is specified by phi. Okay, so phi gives the longitude. Yeah, and as is familiar from geography, longitudes go all the way from 0 to 360 degrees, and no wonder phi also goes from 0 to pi. And of course, you need a reference longitude from which you're going to start counting 0, and that reference longitude is it's the one that passes through Greenwich, the Greenwich meridian. So in this case, that meridian has been chosen to pass through the positive x-axis. Yeah. So the positive x-axis in this setup would go through, I guess, someplace in Africa. I think it's Ghana. So the meridian through Greenwich, I think, passes through somewhere, Ghana, Nigeria, that kind of place. So, okay. Yeah, and then, okay, just to complete this story and so that your picture is clear, then the points this way, pointing this way, the negative x-axis, geographically, where do they point? Towards which place on Earth? Yeah, the negative x-axis. I said this points towards Ghana. So you have to tell me which way this points, or tell me the name for that thing, the meridian.
Is it IST?
Not Indian Standard Time. Sadly, we are not. Our longitude is not. I mean, this longitude is pi. Yeah, I mean it's 180 degrees. Yeah, so we are not that far. We are much before that.
It's the antipodal to Ghana.
Yeah, it's antipodal to Ghana, indeed. So which place is antipodal to Ghana? Tell me which ocean it lies in, first of all. It is some very famous. That meridian has a very famous name.
Pacific Ocean.
Sorry, yeah, Pacific Ocean. Indeed, it's the Pacific Ocean, and that meridian. Well, they do some little
standard line.
It's called the international date line. Yeah, I mean that is called international date line. It passes through some islands in the Pacific Ocean. Of course, for practical purposes, they curve it left and right to avoid some islands. Otherwise, in that island, some people will be on Sunday, and some people will call the same day as Monday. So. Yeah, okay, but apart from this, I hope this picture actually helps you. So please ask me if it's not clear.
Sir, I don't think we are very good in geography.
Okay. All right. That is a nice that you mentioned that. I will then invite you to find yourself a little globe and look in the side opposite to Ghana.
So azimuthal angles.
Azimuthal angle gives you the longitude measured from the x-axis, measured from the meridian passing through the x-axis. Anhad, please ask again if you have not clarified. Okay. Any additional question?
Sir, if we want to identify a point from z-axis, do we leave phi undefined?
Oh, thank you very much. So you have pointed out a serious problem with our coordinate system. It is not covering the entire three-dimensional space in a proper way. So let us say a few words about that, since you have very rightly raised this question. So let me zoom over to that point. So unfortunately, spherical polar coordinates break down along the z-axis. Yeah, along the z-axis, the azimuthal angle phi, azimuthal angle phi, which tells you which latitude, which longitude you are on, is not uniquely defined, right? It can be assigned any value from 0 to 2 pi if you are on the z-axis. So who asked about this?
Sir, Anush.
Oh, Anush Rao. Okay, yeah. So on the z-axis, phi is not uniquely defined. So we say that when a coordinate system does not cover the whole of R3, we need to do some patchwork to fix that. We could use some other coordinate system in that place. All right, where at points where one coordinate system breaks down, you use another coordinate system. I don't want to go into this. I mean, this is basically, if you proceed in this way, this thought process will lead you to a proper definition of a manifold. So I don't want to do that here, but you have pointed out a very important issue, and this is the issue that one has to grapple with, even in physics problems when you are dealing with points where the coordinate system breaks down. But let's not belabor that right here. Any other question or further question about this matter?
Okay, I mean, I had an unrelated question related to spherical coordinates, but not related to this exact thing.
Fine.
In spherical coordinates, is it correct or intuitive or even intuitive to represent, suppose r cap as partial derivative of r comma theta comma phi with respect to r?
Yeah, you're right. So it is possible to think of these as partial differential expressions, or correct. Yeah, r hat is related to partial differentiation with respect to r, and theta hat is partial differentiation with respect to theta. Yeah, this is correct. I am not taking that viewpoint here because that really belongs in a course on tensor calculus or manifolds. Yeah, but you are on the right track. Yes.
My question was like, can we use it as intuitive information?
Yeah, you can use it as infinite, because that is how I defined it, right? I said r hat is the vector directed in the direction of increasing r, holding theta and phi fixed. Yeah, so that what you have said, that is, it is some kind of partial derivative with respect to r holding theta and phi fixed, is smells like the same thing. Yeah, so yes, you can use that intuition. It is basically
But we cannot
correct.
use this in like as a proper thing. Like I cannot apply this.
No, it can be applied in a very proper way. You just need to learn the tools to do it.
I mean,
but,
in our assignments.
No, not in our assignment. No, please, not in our assignment. In our assignment, I want you to use geometry, right? So r hat, theta hat, they can be defined entirely through geometry, not through differential calculus. And that is the definition we are using. So I invite you to please do that, because there is intuition to be gained there. Yeah, so drawing pictures is very valuable. Once you get comfortable with that, we will also take up the purely differential approach. That too is very valuable.
Sir, could
yes,
you please repeat what you meant by coordinate system breaking down?
Let me do that in a simpler example, right? This problem we are facing, see, along the z-axis, I hope you have noticed that along the z-axis, while theta is 0 along the positive z-axis, and negative z-axis, theta is equal to pi. Okay, so theta is well defined. If you give me a point, I can tell you what the theta is. It's either 0 or pi. So there's no problem with theta. Are you okay so far?
Yes.
Okay. Now we ask, for a point which I have marked here, what is the value of phi? That's the question I ask. Okay. Now to answer that question, how do you proceed? You take your position vector, project it down to the xy plane. When you project it, it will come to the origin.
Okay.
And you ask, what is the angle that projected vector makes with the x-axis? Now this projected vector is the 0 vector. So it can make any angle with the x-axis, whichever one you choose. Yeah, so it is not well defined. That is all.
Okay, so you're defining the coordinate system as a tuple phi comma theta, and where
R
phi
theta and
represents
phi.
the rotate. Okay, r theta and phi.
Triple r theta phi, ordered triple r theta phi, where r denotes the radial distance, theta defines the the polar angle of inclination with the north pole, northern axis, and phi is the azimuthal angle made on the xy plane. Is that okay?
Yes, that's
Yeah. I mean, it is like asking a person who is standing on a North Pole to tell you what their longitude is. Yeah, see, every longitude passes through the North Pole. So if you ask the person, are you on the prime meridian, or are you on the meridian passing through Chennai? Are you on the meridian through the international dateline? The answer to all these questions is yes. So there is no clear meridian, no unique longitude that passes through the North Pole. This is the ambiguity. So the map between XYZ and R theta phi is not one-to-one along the Z-axis. So that is the problem. But we can handle this problem. There are ways around it, but one needs to be just aware of it at this stage. Okay, any other questions? Of course, from trigonometry, I can write down a couple of additional formulae from this projection business. Yeah, the projected vector, what is the length of this projected vector, by the way? If I project the vector, position vector onto the XY plane, what is its length, please?
X square plus y square.
Y squared square root, indeed. Yeah, so this is the length of projected vector R onto the XY plane. So that's simply x squared plus y squared under square root. And therefore, the angle phi, the azimuthal angle phi, is given, or its cosine is given by x upon square root of x squared plus y squared. Is that understood how I got that? Yeah. Or if you like, you can also say that the tangent of phi is y upon x. That's another way to look at it. Okay. Yeah. All right. So much for the definition. We can now proceed and write down x, y, and z in terms of r theta and phi. So let me do precisely that. This again we read off from the picture. The vertical coordinate z is r cosine theta. Yeah, I hope that's clear from the picture. This was r and this is theta. So r cosine theta is z. Yeah. Now x is what is x? Yeah, so we are supposed to take this vector. You told me the length of that vector in Cartesian variables, x, y. Can you tell me the length of the same vector in polar variables, please?
X cos phi.
Oops, I don't want to hear any x, y, z. I just want r theta phi. What is the length of this vector?
R cos.
Thank you. It's not r cosine theta. That r cosine theta is z.
Sir, R cap.
Oh, wait. I don't want to know the vector. I want to know only the length of the vector. I want to know the length of this projection.
R sin theta.
Thank you.
R
It is
cos.
Okay, you have all suggested things. The correct answer is r sine theta. See, think of the plane through the longitude that passes through the point P. In that plane, we have this vector. I can take its vertical projection. I can take its horizontal projection. The angle here is theta. So from simple trigonometry, the horizontal projection will have magnitude r sine theta. Okay, so r sine theta is equal to x squared plus y squared square root thereof. Are you with me on this? Any question about this observation? Okay, great. So then I can now write down a formula for x. Yeah, x is this distance. So that distance, can you please tell me how much is it in terms of r theta phi?
Will you repeat?
Srinish, could you repeat your question?
What did you ask just?
My question was, I want to write, see, we wrote z in terms of r and theta. Okay, we have achieved that. I want to write x in terms of r and theta, r theta and phi. I'm asking.
Just say that x is square root of x square plus y square cos phi, which is r sine theta cos phi.
Thank you very much. R sine theta cosine phi. Yeah, because after all, I'm just looking at this right triangle. This right triangle. This angle is phi. The hypotenuse has length r sine theta, and this angle is phi. So the adjacent side is hypotenuse times cosine phi. So proceeding in that manner, what is y? Please offer your suggestions.
It would be r
R
sine
sine
theta sine.
theta.
R sine theta times
Sine
Sine.
phi.
Phi.
sine phi. Thank you very much. Okay, so I think you're getting the hang of things. Yeah, so we are just chasing the angles and writing the answers. That's it. So yeah, so any question about how we wrote this down? The hypotenuse is r sine theta in length, and the angle is phi. So the two.
Theta and phi will be functions of time, right? Theta and phi, they are
See, right now we are considering a point or a particle that is at a fixed point. It's not moving. But if it moves, of course, all of these are functions of time. That is indeed correct. But any one instant of time, you have one theta, one phi, and one r to describe the particle. Okay. So that is what we have written here. And you can, of course, invert these formulae and so on. I will leave that game to you. Okay. Any question about this geometric setup? Because you're going to use it in your answers in the next problem set as well.
Sir,
Yes,
in
please.
the above formula, we have phi equals r cos something. So r cos has range 0 to pi, right? So how do we...
R cosine. Okay, no, the cosine function goes from 0. I mean, the periodicity is 2 pi. So, okay, you are saying you are choosing some fundamental domain for the R cosine and so on.
yes.
Okay, I don't want to. You are supposed to extend it. Let's discuss this separately. Yeah, how you define R cosine and so on. The sign does matter. Let me, okay. Yeah. See, you are quite right that this point and that point have the same cosine. And for that reason, you are cutting off this function here and saying the arc cosine only goes from 0 to pi. Yeah. So, okay, that is accepted. But here I need further information. I need to tell in which quadrant I am located, and based on that, I need to define phi. Okay, so I encourage you to think more carefully about this. Depending on xy is a point in the plane. So depending on which quadrant it is in, you will need to work carefully and define the angle phi. You will need to make sense of this arc cosine function. So I would like you to give a little bit of thought to that. If it doesn't make sense, please ask once again later on. But is the overall picture clear?
Yes, sir.
Okay. Thank you. But you are right. The arc cosine, there are subtleties there. You need to pay a little closer attention. Okay. All right. Okay. So let us now proceed to the unit vectors. Or vectors. So we are going to define the position vector of the particle, which is located x, y, z, as r. R boldface, and that is simply x hat plus y hat plus z hat. And by definition, that is also r times r hat. Now, from the figure, it is possible now to express these r hat, theta hat, phi hat vectors. Now, first of all, what are their definitions? R hat is, by definition, is the unit vector pointing in the direction of increasing r, holding theta and phi fixed. Okay, so that's illustrated over here in this picture. This is our point. This is the position vector, and the radially outward pointing unit vector is called r hat. Now, the polar angle, of course, increases this way. So if I go to the plane of the longitude through this point and look at a vector tangentially downwards that way, that is the direction of theta hat.
Phi hat.
And phi hat is also interesting. I have drawn it in a particular way. Let me explain it. To motivate it carefully, let us first take this radius vector, the position vector, project it onto the xy plane. Okay, so I projected it. Now on the xy plane, you have the angle phi defined, and the unit vector in the direction of increasing phi is called phi hat. Okay, so now the phi hat at this point is the parallel translate of this phi hat. Okay, so it is, it is sort of into the board, into the, my picture is not that good. It's supposed to be parallel to this one. Yeah, so, okay. So, Onkon, are you following? Okay. Yeah, there was another question.
Sir, is it phi cap perpendicular to xy plane?
No, phi cap lies in the xy plane, so it is parallel to the xy plane. Yeah, I have taken this vector and parallelly moved it upwards. So definitely it is not perpendicular to the xy plane. It lies in the xy plane. Are you able to visualize this?
Yes, sir. Then is it perpendicular to that r sin theta?
Is it perpendicular to this projection vector? Indeed, it is. It is perpendicular to that. Yeah. Okay. Yeah. And furthermore, the picture is also supposed to convey, I think from the picture, it is already very clear that the radially outward pointing vector is perpendicular to this one. So r hat and theta hat are perpendicular. But not only that, also phi hat is perpendicular to both of those. Yeah, now, I mean, all this is also related to a problem in the homework, but that problem is a purely algebraic calculation. What we are doing right now is a geometric visualization to derive these formulae. So it is possible, just like we did in plane polar coordinates, to get formulae for r cap, theta cap, and phi cap in terms of x, y, z unit vectors. Okay, so let us do this in one example. Let us do it for the r cap vector, which is in some ways the more complicated one. What has happened? Okay, so my aim right now is to derive the formula for r hat, okay, purely to geometry and trigonometry. So let us examine it a little carefully in this picture. So this is my origin, this is my radius vector. So the r hat vector points radially outwards. Yeah, now I go to the plane containing z and r vector. Okay, so that is the longitudinal plane through my point of observation, this point P. Yeah. Now in that plane, the vertical direction makes an angle theta with respect to r cap. And therefore, we may resolve r cap in that plane. Its vertical component is going to be cosine theta, of course, times z hat. Are you clear how I got the z component?
Can you please repeat again?
Yeah, sure. Okay, see, what is the meaning of the coefficient of z hat here? It is simply the projection of r hat on the z axis. That is all it is. Yeah, somehow my internet connection is a bit shaky. Moment. Yeah, so while this tries to connect, yeah, see, we want to resolve R vector into its X, Y, and Z components. So the first component we find is the Z component, and that we just find by projecting onto the vertical axis. We already observed that the R vector makes an angle theta with the Z axis, and therefore its component in that direction is simply cosine theta. So Oncon, do you follow that? I said it in words.
Yes.
Okay, great. Now, while I continue to fix my, sadly, this internet is not working. Actually, I don't know what the matter is. But while I fix it, let me say everything in words. Yeah, that vector we want to find the X and Y components. So how do we proceed? We project the R vector onto the XY plane, and that projected vector has length R sine theta. Okay, this is something we learned a short while back. Yeah. Now that R sine theta projection vector has X and Y components. We need to find those X and Y components. Those X and Y components are given by R sine theta cosine phi and R sine theta sine phi. Okay. This is not good. Let me try again. Okay, thankfully, I've been able to get this back on track. So Oncon and others who were asking about how I got these components, I said it in words. Please see whether you follow. The X component is gotten by first projecting this vector down to the XY plane. Now that is this vector. Recall that it had a length R sine theta. Now we want the X component of that. So that is R sine theta times cosine phi. Yeah, of course, R is 1 in this case because it's a unit vector. In R hat was a unit vector. So, okay, I should do this more carefully. I'm sorry. So this is R sine theta, but what I really mean to write is that this vector, which is the projected version of this unit vector R hat onto the XY plane, at this point makes again the same angle phi with the X axis. And therefore, this component is given by sine theta cosine phi. Did I say that clearly? Did you follow? Or any question about that? Okay. And we similarly have the Y component. That is, you take this vector which has length sine theta and project it onto the Y axis. The angle there is of course the complement of phi. So you will get the sine of phi. So in this manner, I have derived these three components. Any question about those components? Please feel free to ask. Okay. Okay, very good. Now one can similarly play a similar game with a little bit more trigonometry. Actually, it's not that bad. To get your theta hat and phi hat vectors expressed in terms of x hat and y hat. Okay. Now the phi hat vector is particularly easy because phi hat points this way. Yeah, on the xy plane. So it has only x and y components. So this goes back to a question somebody else asked previously. So there is no 0 times z hat. There's nothing in the vertical direction. It lies in the xy plane or it's parallel to the xy plane. And its components, I invite you to check, are minus sine theta and cosine theta. That's
No,
just
but
like, yes, please.
Are you, don't you need to prove that phi hat lies on the XY plane?
Yeah, see, our job here to find the X, Y, and Z components of a vector. Now, to find the components of vector, the original vector, of course, was located here. Yeah. And I would have to resolve it with respect to axis positioned there. But for my convenience, I can parallel translate that vector down to the XY plane. Yeah, observe that the vector phi hat lies in the XY plane. Therefore, conclude that the Z component is 0. And then find the X and Y components using an axis, XY axis, which is centered at that point. So that's what we are doing. We are freely moving our axis around, moving our origin around according to our convenience. So Onkon, are you following? Okay. Yeah, so you will have heard in the discussion we have had yesterday, I mean, last week as well as today, this repetitive use of the way of parallel translating vectors. So that is a very, very important tool that we are using. We have an intuitive idea of what it means to parallel translate things in Euclidean space, and we are simply exploiting that. A deeper understanding of this was achieved by Riemann, and that led to Riemannian geometry. So, but here we do not need those things. I want you to get comfortable with parallel transporting vectors and finding their components using trigonometry. So I will leave as an exercise to you to get the theta hat.
No, deeper meaning. Which one's deeper meaning?
No, could you say that again? I didn't.
You said that something that Riemann found the deeper meaning of this what?
Yeah. He explained how you do parallel translation of vectors, not in Euclidean space, but in curved spaces, like on the Earth's surface. Yeah, the Earth's surface is. Yeah.
Okay.
So this is a very deep insight of Riemann, how to generalize this concept of parallel translating vectors to curved spaces. I mean, not just Riemann, also Gauss. Many people are involved. Yeah. Yeah. And the idea extends beyond 2 and 3 dimensions. So without telling you, we are actually doing quite sophisticated things here, but in the very concrete context of Euclidean space and particle motion there. Okay. Yeah, I leave it as a little game for you to find out these components of phi hat in terms of X, Y, Z. Okay. Any further questions about how we did this geometry and trigonometry? Yeah, I very much encourage you to draw these pictures yourself. And I mean, using, of course, what we have done here, and rederive all these formulae for yourself. It is a lot of fun, and will provide you a lot of confidence as well. Okay, so if I may, yeah, there was some question about where can I look up more on coordinate systems. See, such things are discussed in many geometry books, as well as books on mathematical methods in physics. Yeah, I mean, if you want me to suggest some book, I can suggest. Yeah, there's one by. Or maybe let me put it in the list of books. Yeah, let me give a good reference. But a quick and dirty reference. No, I shouldn't say quick and dirty. There's a book by Kreisig. No, I take back that word, quick and dirty. SZIG. Yeah, Erwin Kreisig. I think it's called something like mathematical methods for scientists and engineers, or something like that. Yeah. Yeah, just to name one, but there are more such books. Okay, now I want to briefly discuss one more concept in our whirlwind tour through the mathematics concepts that we use in our discussion of classical physics, classical mechanics here. This is presumably something you are have encountered before. I just want to very briefly recall a few things about power series. So let's talk about the Taylor series for one variable. Yeah. So by the way, for the answer question in problem set 3, you are given these 3 formulae. You don't need to rederive them. You can take these 3 formulae, but then you are supposed to verify basic properties of them, such as their orthogonality, orthonormality, and so on. Okay. So that is purely calculation using dot products and so on. Okay. For a reason, I do want to introduce some terminology here on Taylor series. So given a function of one real variable, f of x, that is continuous and hopefully differentiable a few times, we are interested in approximately evaluating it in a neighborhood of a point x naught. Okay, so that is our objective. We want to approximately evaluate it. I'm taking a very pragmatic view. So by continuity, the value of the function near x is good, well approximated by f of x naught. Okay, so because it's continuous, the values nearby are well approximated by f of x naught. Yeah, so this is of course our 0th order approximation to the value of the function for x near x naught. Okay. The next possibility, if you want to get a better approximation, is to approximate f not by a constant function. See, this is approximating f the function by a constant. Yeah. The next approximation would be by a linear function near x naught. And which linear function? Well, it is natural to take the slope of the function, because that is in some sense the best linear approximation. Yeah. So so we take the slope of this linear function to be the derivative of f at x naught. So I will go through this relatively quickly, because I think these are things you would have studied in school perhaps, or also currently in college. But the viewpoint may be slightly different. Yeah, so assuming f is differentiable at x naught, we will approximate the graph of f by the tangent through the point x naught comma f of x. Okay, so this leads to the first order or linear Taylor approximation, which I have written here. F of x is approximately f of x naught plus f prime of x naught times x minus x naught. Okay, so this is an approximation. If you want to improve, you will have to add more terms. This is illustrated in the picture, which I think you are all familiar with. I have a point x naught, a nearby point x, and this is the tangent to the graph of the function at x naught, and the slope of that tangent is the differential coefficient f prime of x naught. Okay, so we have simply used this observation. Now, if you want to go one better, yeah, let us see what you do. First, let me introduce some notation. Now, to indicate that x minus x naught is small, we will denote it by delta x. Okay, delta x is a shorthand for x minus x naught, and so we will and we will also call the difference of f from its value at x naught by delta f. Okay, so I have defined delta x and delta f. So from this formula, equation 36, we can write this formula 36 as simply saying that delta f is approximately f prime of x naught times delta x. So this is simply an approximation. Okay, now I want to introduce another term. It is called the differential of f. Okay, so the differential of f. The differential of f at the point x is defined as df. It's written df, and it is defined as the derivative of f times dx. Dx is called the differential of x. Okay, so this is my definition. Okay, I have x, a variable. I have some symbol called dx, that is called the differential of x, and using it, I define the differential of f. Okay, this is not any approximation. This is an equality. Furthermore, you have the concept of the derivative df dx, which is defined using your previous objects. as a limit of delta f by delta x as delta x goes to 0. Okay. So, so for instance, if you have a function sine x, we can write its differential d sine x is a derivative of sine x, which is cosine x times dx. Okay. So in physics, we very frequently use the differentials. And so I just want that language and the notation to be clear to you, not just in physics, also throughout differential geometry and other areas of mathematics. Okay, so the differential of a function is also called a one form. Okay, so that term may be used sometimes. Just I just want to mention it. Okay, now going beyond this. By the way, from the picture, you will see that, of course, the tangent to the curve provides a good straight line approximation to the function. But if you want to do better, you would the next best thing would be a parabolic approximation to your graph of the function, and that leads to the next Taylor approximation. So I won't go through each of the steps, but let me just mention that more generally, if f is n times differentiable at x naught, then we have the nth order Taylor polynomial approximation for small x minus x naught. So I just write down this Taylor series. I shouldn't have said series, it's a polynomial. And I'm regarding it as simply an approximation here. Yeah, f of x is approximately f of x naught, constant approximation, f prime of x naught, x minus x naught, linear approximation, and then you have the quadratic Taylor approximation, second derivative times x minus x naught squared divided by 2, and then you got yet more correction terms up to the nth order derivative. Yeah. Okay, so this is what we will mean by the nth order Taylor polynomial or Taylor approximation to f at x naught. Yeah. Any question about what I've said so far? Okay. Now for a few more remarks. For many of the functions that we encounter in our studies, the Taylor series obtained by letting n go to infinity in the previous formula remarkably converges to the function f for x in a neighborhood of x naught. So if this series extended to infinity converges to the function in a neighborhood of x naught, then we say that such functions are real analytic. So that is the name given to functions which admit a convergent Taylor series. Yeah, a real valued function that is continuous in some domain is said to be of type C0. Okay, if it is simply continuous, we just say it is C0. If it is also differentiable with continuous first derivative, we say it is C1. So basically differentiable once with continuous first derivative. And similarly, we can extend that concept to CK functions. Can continuously differentiable k times. So if it is continuously differentiable k times for all k, all positive integer k's, then we call such a function smooth. All right, it's called smooth if all derivatives exist and are continuous. Okay. So a function whose Taylor series converges to the function in some domain is called real analytic. Okay. So function that is called which is all derivatives exist and are continuous, that is called C infinity, infinitely differentiable. A different notion is real analyticity, which is the convergence of that series. Okay, so that kind of function is called C omega. So these are some names given to these types of functions. They have very deep physical significance. Yeah, in mechanics.
I could not understand C omega.
Yeah, C omega is simply a name for function whose Taylor series converges to the function in some domain. Okay, so you pick your domain and your function is already specified to you. Values are known to you. You compute its Taylor expansion. How do you compute its Taylor expansion? Keep on differentiating. Yeah, compute first derivative, second derivative, third derivative. Assemble all those derivatives in a series. Add up all the terms. If that series converges and converges to that function, then we will say that function is C omega or real analytic. Is that clear, Ankon?
But if a function has a Taylor series, I mean, all functions do not have Taylor series, right?
Sadly, yeah. Like a discontinuous function doesn't have a Taylor expansion at the point.
So those functions which have Taylor series, then the Taylor series must converge to that function.
Oh no, it's not the case. You may have a Taylor series that does not converge to the function, sadly. So there are lots of functions which have a Taylor expansion, because after all, to get Taylor expansion, you simply go take the function, keep on differentiating, right? I mean, you're not adding the terms. You're not asking about the convergence of that series. That's a much deeper question. You can simply write down a Taylor series. Whether that series converges is one question, and even more important question is whether that series converges to the function you started with. This may fail, sadly. Okay, so
can you give an example?
Oh, certainly, yeah. So you take the function e to the power of 1 by x. All right. I invite you to compute the derivatives of this function. Okay, so first of all, what is, so that is f of x, right? What is f of 0? Okay, let me put minus sign here. Yeah, so this is my function e to the power of minus 1 by x. What is f of 0?
0.
Good. So the function vanishes at the origin. What is f prime of 0? I'm computing the Taylor series. All right. So I need to compute f prime of 0. Yeah. You compute the derivative, right? You differentiate this thing, you will get some 1 by x squared times e to the minus 1 by x. Are you okay with that? Can you tell me what is f prime of 0? Okay, let me do it. F prime of x is equal to e to the minus 1 upon x times derivative of that, right? So you'll get 1 upon x squared, right? What is the limiting value of this quantity as x goes to 0? This coefficient will go to 0 much, much faster than this thing diverges. So I hope you will agree with me that f prime of 0 is 0. Are you following? I invite you to compute this limit. Please ask if you are not clear.
Sir, f of 0 is 0, but we have to like define at 0, right? It is
In a
undefined at
limiting
0.
sense.
Yeah, in a limiting sense. Yeah, I'm defining this function at 0 in a limiting sense. All right. And similarly, I'm computing all these derivatives in a limiting sense. Now, all these, so proceeding in this way, I claim that the second derivative also vanishes at the origin.
All of those
Yeah.
All of the derivatives 0 vanish.
Yeah, all the derivatives at the origin vanish. Okay, this is true because it will have always this prefactor times some Laurent polynomial. Yeah, but always that Laurent polynomial will diverge much more slowly than this. Yeah, this is a damping factor that goes to 0 very, very fast. Okay, so all of these polynomial corrections are irrelevant. All derivatives vanish, and therefore let us now, with this newfound knowledge, I will write the Taylor expansion of this function at the origin. So Taylor of x, yeah, is 0 times yeah, I mean, that's the, what was the Taylor expansion? It was defined as f of 0 plus f prime of 0 times x minus x naught plus f double prime of 0 times x minus x naught squared by 2 plus dot dot dot, right? This term is 0, next term is 0, third term is 0, all terms are 0. So the Taylor series for this function is the 0 function, and all terms are 0. You can add all those zeros and still get 0. So the Taylor series for this function is a convergent series converging to the 0 function. Sadly, it is not the function we started with. Okay, so I have demonstrated for you a function which has a Taylor expansion, but the Taylor expansion does not converge to the function. So this function is infinitely differentiable. All derivatives exist. So it is C infinity. Yeah, it is C infinity, but it is not C omega. It's not analytic because the derivative, sorry, the Taylor's expansion doesn't converge to the function. Yeah, I went through this a bit fast, but I hope the idea is conveyed to you. Any question? Okay, I need not have spoken about this, but I think it is worth having some basic facts in your mind, because remarkably such subtle differences show up in physics. Yeah, in understanding the behavior of mechanical system, whether it behaves regularly in a random way or some kind of chaotic way, these subtle issues, it turns out, play an important role. Yeah, but it's not something we can discuss in detail in this course. Yeah, so anyway, I encourage you to calculate the Taylor series for some simple functions like 1 by 1 minus x or exponential of x. Yeah, yeah. So I think that is something you're familiar how to do. Simply differentiate it, evaluate the derivative, and put them together in a series. Okay. Any questions before we halt?
I had a question regarding the problem 1 in the problem set, and
okay.
There was a particular part where we were asked to interpret the coefficients of r hat and theta hat.
Correct.
What are we
velocity.
intended to?
Yeah, you have to describe them. You have to describe them. You give a nice name or say in words. Yeah. So I don't want to say more. You have to do a similar thing for the acceleration. So see, I'm not asking for some standard name, yeah, or some name from the literature or some book. You describe it using the formula in front of you. All right. And the type of words we have been using. We have been using words like radial. We have been using words like azimuthal, tangential. Yeah, you can use such words. Try to come up with a nice description. Is that okay, Nirja?
Yes, sir. Yes, sir. Thank you, sir.
Okay. All right. Yeah. So anyway, good luck with that. Yeah, there is no, yeah, it's not that you have to find some fancy name for this. You just describe it using what you see. There are, of course, some derivatives there. So whatever terms you use have to convey those things. You can say in words what you have calculated. That's also all right, with a little bit of inspiration. Okay. Any other question? Okay, if not, we will stop here and have a good afternoon. We will reconvene on Thursday.
Sorry, sir. I had a
Yes.
question.
Yes.
Sir, about the homework, there was this question of finding out. There was, I think, I could not understand the language actually. Leaving like U is increasing, but V is not increasing. I could not understand that language in problem 2, I think.
No. See, that is only some background. We are defining some two new variables U and V in terms of X and Y.
Okay.
And I mean, that's like saying R and theta are defined in terms of X and Y.
Yes, sir.
Having defined these, I am saying that vectors in the direction of increasing U holding V fixed can be expressed in a certain way. Okay.
Sir, is that required to find out in the homework?
No. You are not expected to find that out. That formula is given to you.
Okay, sir. If we are not required to find that out, could you please show me the derivation, if possible?
That derivation involves those partial derivatives, which I think you or somebody suggested some time back. It involves that other approach. Using that approach, one can get that formula that vector U is equal to some A x hat plus B y hat. That is a restatement of a formula got using partial derivatives. So I am avoiding doing that. So you will learn it afterwards, or we will do it later on. So Ryan, I'm going only half answer. Is that okay?
No problem, sir. And
yeah.
That in that problem only.
Yes.
Could you? Yeah. Is it possible to explain what is required to do? Like what is asked?
Yeah, you are asked to. You're given two vectors U and V, which are linear combinations of X hat and Y hat. Yes. You're asked to check or find out under what circumstances these vectors U and V boldface are orthonormal.
Okay, sir. Thank
for
you
that-
very much.
Yeah, now you proceed from there.
Okay, sir.
And then I've asked you to interpret the answer that you get in terms of that matrix. Okay, so that's a separate thing you have to try to do. Okay, any further questions? All right. So but you must use all the conditions you get, yeah, to say what you understand about that matrix. Okay, good luck. So we will halt here. Have a good day.